we discussed that matrices can be rows in linear set of equations, as we introduced a moment ago, or they can be data sets established the columns or in the rows. Doesn't matter, like it's the same data anyway, like however you look at the data, but the columns and rows are going to represent some other things. And we also mentioned, which we will open up probably very soon, that matrices can also represent spaces or spaces that the data live on, or spaces that an operation can project one input to. But long story short, in this video, we will introduce different types of matrices. Of course, there are probably infinite, countably infinite types of matrices. I will, in this video, introduce different types of matrices from their shape point of view. So to start from the shape, we'll start with square matrices, which are more simple, more to the level that we introduce the operations, and non-square matrices. So first of all, from the square matrices, we have invertible versus singular matrices. A moment ago, we introduced that a matrix can be linear set of equations that take inputs and give you another vector, and we can try to solve for that. Or matrices can be operations that take vectors and vectors in one dimension and take it in one dimensionality and take it to some other location. In order to find the answer to these solutions, we um, take the inverse of this matrix. If the inverse can be taken, it is called an invertible matrix, and it's called when the A inverse exists. And we argued last week that the inverse takes if the matrix takes warps the space in some way, its inverse can take it to the other way. Similarly, a singular matrix will not warp the space, but it is going to collapse the space to some location, so to some subspace, which definition of which we have not provided yet, but it collapses, right? So if it collapses, several different points go into the same point, so there's no coming back. The name for such matrices where it collapses and there's no coming back is singular. So when we have an invertible matrix, we are talking about, from the finding the solution of a linear set of equations perspective, we can actually find a result um, from two lines. Each and every one of the lines form um, one different line, and these lines intersect. And from the intersection of these lines, we can find the point. So from invertible square matrices, there exists a single unique solution. The first row of this matrix and its solution provides one line, and the second row provides another line, and the rows of these matrices intersect at one point, and there's a single solution. Singular matrices, however, can have either no solution or infinite solutions. If the determinant of this matrix is zero, it means that it collapses and there's no solution. When determinant is zero, look at these two examples, for example. So 1, 2, 2, 4. It's actually, it looks like it is providing two lines, but it is actually the same line. When you look at it, x plus 2y equals 3, okay, and 2x plus 4y equals 6. So this is actually the same line. We are um, reducing the set of solutions from two-dimensional space to this line, x plus 2y equals 3, this line. So therefore, the number of solutions here are infinite. There are infinite number of solutions. The same ax equals b form can also be set with a singular matrix, but then we can have no solution. Look at this example. X plus 2y is 3. 2 x plus 4y equals 1. These two lines, there are two different lines. They are not the same line now, and there are no solutions. If we were to look at this first example in which we are faced with infinite solutions, we have x minus 2y plus 3 equals 0. That's one line. And guess what? The second line is also showing the same equation, and we have infinite solutions. There are infinite points on this line, and therefore that's why we call it infinite solutions. However, when we have the same coefficients, x minus 2y, it doesn't need to be the same coefficients. You will see in a second that what makes this matrix singular is that the slope of this line becomes the same. Please note that I am just displaying on a two-dimensional space the lines, whereas linear algebra lives in multiple dimensional spaces and worlds. So in this example, x minus 2y plus 3 equals 0 is one line, and 2x minus 4y plus 8 is another line, the red line, but this time it has a different intercept from the center, and these two lines do not overlap. Therefore, we call it, there are no solutions. Another example of a singular matrix.